Okay, so let's pick up back up with metric spaces. And we're interested in what does it mean for things to converge in metric spaces, and how do we decide if things converge in a metric space. This pen doesn't look like it has much life left in it. Okay, so the definition, I mean, most of the definitions are almost identical to what they have always been. We just have to explicitly mention the metric. And the metric was always there in the past. We just didn't call it a metric. We just sort of wrote down explicitly what it was. So we have a sequence. UN in some metric space. Okay, so the metric space is defined by the collection of objects and by the metric itself. Okay, and we're going to say that the sequence converges to some point in this space. If, all right, I could write you down an epsilon and star definition here. The crux of it is the distance between these UNs and this U is going to 0, right? As n increases, the distance between these two things goes to 0. So the way I can write that as the limit of rho UN and U is equal to 0. And of course, if you need to, you can unpack this further as an epsilon and star type definition. So we have the concept of convergence. One of our useful tools for assessing convergence in the past has been the idea of the Cauchy sequence. So we can still define Cauchy sequences. We shouldn't make assumptions about what Cauchy sequences do now. We know that things that were true in Rn may not be true here. We've got to recheck all of that. But we can certainly write down the definition of a Cauchy sequence, which seems like a potentially useful thing to do because this has been useful in the past. So a sequence UN in a metric space A row, all right, is Cauchy. Okay, if. And now we're going to write down the usual definition of a Cauchy sequence. So if for every epsilon bigger than 0, there exists some n star, such that if n and m are bigger than n star. So what are we trying to do? We're trying to say as long as we're far enough down the sequence, we can take any two values in the sequence, however far apart they are, and the distance between them should be made less than epsilon. So the only difference here is that where before I would have explicitly written, the length of UN minus UM, now I'm going to call this the distance. And what we hope is that there might be some connection between this happening and this happening, because of course this was nice in that it didn't require us to know or be able to guess at what the limit was. Just working with the sequence itself, we could decide if there's convergence. So there is a connection between them right away. So what we had before was basically an if and only if. Convergence is convergence in Rn completely equivalent to being a Cauchy sequence. I can't straight away write down an if and only if. So I'm going to write down one direction. One direction is easy. And then we'll think about the other direction. Okay? So if a sequence converges, then it's going to be Cauchy. is going to be not too hard to establish, just straight from the definitions. Okay, so we start with something that converges. So we have a sequence in our metric space, and it converges to something. And then I just write down what that means. Knowing that we're working towards the goal of recovering the statement that this is a Cauchy sequence. So we pick an epsilon. Well, we know there exists some n star such that if n is bigger than n star, then the distance between un and u is less than epsilon. Now what do I need? I need to look at not just a un, but a um. I need to compare two of these things. I've got a good candidate for my, I need an n star. Well, this is the obvious candidate to use as my n star. Why try something more sophisticated when we haven't tried the easy thing yet? So let's consider any n and m now bigger than n star. And we need to look at the distance between these two terms in the sequence. Okay, so what tools are at my disposal to go from something that looks like this to something that looks like this? Triangle inequality, no different than what we would have done in the past, but now we're going to use a general metric instead of explicitly using a Euclidean metric. But we still have a triangle inequality, so this is still true. We go from un to u, and then from u to um. Okay, and since both of these guys are past the magical n star, both of these distances will be less than epsilon. So indeed, I can make the distance between any two points in the sequence as small as I want. So we say, great, this is a Cauchy sequence. And of course, that means that if we ever come across a sequence that's not Cauchy, we automatically know it's not convergent. Now the other direction. The other direction, the proof is not going to follow this easily. In fact, with the information we have so far, the proof isn't going to happen at all. It's just not, it just isn't automatically true, and I don't have to go to looking for exotic examples to show you this. I can give you a really, really simple example to show you this. So what we knew before was that we had this if as an if and only if in the special case where this was Rn and this was our Euclidean metric. Okay? I can go simple. So let's do a simple example. Let me take a subset of Rn. Just the interval from 0 to 1, open interval. And I'll take our usual metric. And I can write down a Cauchy sequence in here. Okay. If I have a sequence that converges, it's definitely Cauchy. We know that, we just proved that. I'm going to go the other way now. Let's consider the sequence un equals 1 over n. Okay, so this is a sequence in my metric space A. Everything in here is between 0 and 1. And in fact, this is a Cauchy sequence. It's not hard to check that this is Cauchy. So if we let epsilon be bigger than 0, and let's say that n is bigger than m, just to pick something, then what do we have? un minus um equals 1 over m minus 1 over n. All right, if I do this in the right order, I can drop the absolute value signs now because I know there's an order to these. This is less than or equal to 1 over m. And I can certainly force this to be less than epsilon. So this is less than epsilon as long as n bigger than m is bigger than 1 over epsilon. So this is my n star. Okay, so therefore, un is certainly Cauchy. So the next question we have to ask is, does this sequence converge? So you're looking at it, you're thinking, of course it converges. It converges to what? Zero. Well, that's a problem, though. Zero doesn't exist, right? So these are the only objects that I have that exist. This is trying to approach something that's not there. So actually, there's no limit, not in this metric space. If I replaced this with Rn and used the same metric, then yes, it would converge. It would converge to 0, and 0 would be in my metric space. 0 is not in my metric space, so this is not convergent. Okay, so since 0 is not in A, this does not converge in my metric space. Okay, so an if and only if is not automatic here, but we kind of still like to have it. We'd like to have of this tool available to us of Cauchy sequences, an easy way to check if things converge. So what we end up doing is we just define the spaces we like to be spaces where Cauchy sequences converge. I mean, if I made this a closed interval, we'd be in business, right? So I can certainly come up with metric spaces where Cauchy sequences converge. Just it's not true of all metric spaces. So we give a special name to metric spaces where Cauchy sequences converge. We call them complete spaces. So we're going to say that a metric space is complete if all Cauchy sequences converge. So this is an example of a metric space that is not complete, right? So our last example is certainly not complete. But for example, if I changed A to the reals, or even if I just changed it to the closed interval, this is complete. And there are plenty of other complete metric spaces out there, including some very useful ones. So another one, this one we're going to see pop up again over the next few weeks. We'll try to work towards some examples working in this metric space because this is really a practical one. Let's consider the metric space CAB. This is going to consist of all continuous real-valued functions on the domain A to B. Okay, so this is all functions of the form. They take the domain A, B and map them into the reals, okay, such that f is continuous. I need, in order to talk about Cauchy sequences and convergence, I need a metric. So the metric I'm going to put on here is a metric induced by this norm. This is going to be the infinity norm, so the maximum of the absolute value. This is a well-defined object because I have taking the maximum of a continuous function on a closed bounded domain. So this is fine. I can write this down. And then my metric is going to be just the maximal difference between f and g. And this is a complete metric space. So if we want to ask, is this complete? Well, let me just ask the questions. We're not going to go through all details of all of these things, and some of them are really easy to verify. What things do I have to check here? What's that?
Every Cauchy sequence.
I would have to check every Cauchy sequence converges. What else to make this a statement true?
If this is a metric.
If this is a metric, yeah. So I should check if this is a metric. Or one way to do this, I said this is a metric induced by a norm. I should check if this is a norm, but also I should check if this is a vector space, right? If this is a norm on a vector space, then we can induce a metric automatically. So these things aren't really hard to check, but it's just always worth being aware that these are assumptions that we're making when we make a statement like this. So should check that, okay, that CAB is a vector space. Okay, there's a list of like 10 things that one has to check there. None of which is hard to verify. They're all very simple statements. So we should check that this is actually a norm. Okay, again, there's 3 things to check there, none of which is hard to verify, but we just don't want to assume, we want to verify. And if these are true, then we know that rho is a metric. And then lastly, we should say what happens with Cauchy sequences. Do they converge? Okay, so do Cauchy sequences converge? The good news is we're playing with continuous functions defined on a closed bounded interval. That's important. And that means continuity is uniform continuity, convergence is uniform convergence, Cauchy sequences are uniform Cauchy sequences. Okay? This is back to doing calculus on the reals. Okay, so since all of these are continuous, and the domain is closed and bounded, now suddenly we're in the situation where we have uniform Cauchy sequences. So each Fn is uniformly continuous. And we have a uniform Cauchy sequence. Okay, so what can we do with this? Well, first of all, for fixed x, Fn of x is just a sequence of real numbers now. It's a Cauchy sequence of real numbers. It certainly has a limit. So we can certainly define this limit. And indeed, we have uniform convergence because we have a uniform Cauchy sequence. Right, that just means that the same n star works for every x in the domain. Okay, and then we're basically in business. So what do I need to verify? I just need to verify that this limiting function is a continuous function. Right? Without uniform convergence, it may not be a continuous function. We can write down examples of continuous functions on, say, on open domain, where each function in the sequence is continuous, but the limiting function may not be continuous. But because we're on a closed domain, we have uniform convergence. None of those bad things happen. So what do we know? We know there exists some, let's call it n1 star, such that if n and m are bigger than this thing, and x is in our domain, right, then fn of x minus fm of x is certainly less than epsilon. We also know that each fn is uniformly continuous. So we can write down continuity. That's important, right? The fact that this is a Cauchy sequence is important. The fact that we have continuity of each function in our sequence is important, so we can write down that fact. So also, each function in our sequence is uniformly continuous. Okay, so what does that mean? That means there exists some delta greater than 0, such that if x minus y is less than delta, then fn of x minus fn of y is less than epsilon. And then we just have to string this together. So let's let f of x minus f of y, we break this down in terms of things that we think we can work with. f of x, NSF n of x, fn of x, let's bring in the fact that it's Cauchy, minus f m of x. Let's see, is that the way I want to break it down? I'm going to switch to y here first. Let's bring in the fact that it's continuous. All right, now we need to pick an n star, fix our n star big enough that we can make these as small as we like. So let's pick n to be bigger than n star. And that means what? That both of these, because we have uniform continuity, the same n star will work for both x and for y. So both of these can be made less than epsilon. Sorry, f of y. Now, we need a delta. Delta is specific to each n, right? Each n will have a different delta, but we've fixed our n now, so we can now choose the delta corresponding to this n. Fn being continuous gives us a delta. And we know that if x minus y is less than delta, then fn of x minus fn of y can be made less than epsilon. Well, we put that all together, and what do we have? That we have that for x minus y less than this delta, right? And again, there's only one value of n, which is fixed for which I'm using that, so I have a fixed value of delta. I wouldn't want to start mixing, matching different n's and m's in here because I'd get different deltas. But with this all fixed, I can make all of these less than epsilon and say, great, indeed the limiting function is continuous. So indeed, we have a complete space here. And that's great news because a lot of what we want to do as applied mathematicians is play games with continuous functions. Lots of processes are described by continuous functions. We're interested in maybe approximating solutions to these things. So now if we have some iterative method or some sequence that we're trying to use to approximate it, and if we can show the sequence is Cauchy, now we know, great, it's going to converge to something, and that something it converges to will still be continuous, which may be what we need for things to be physically meaningful. So we're going to say, great, indeed, CAB is complete. So this is a useful space that we can play games with. So to take another example, we take this function, 1 over nx plus 1 on the domain 0 to 1. We could ask if this is a Cauchy sequence. So is this Cauchy in, we need a metric space, so in the metric space, the continuous functions on 0 to 1. These are all continuous functions, right? For each fixed n, I get a continuous function here. I don't have a 0 in the denominator. That's not a problem. So it's certainly true that each Fn lives in my metric space, so that's good. But if we want to ask if it's a Cauchy sequence, well, we need to look at the distance between 1 over nx plus 1 minus 1 over mx plus 1. We'd like to show that if n is far enough down our sequence, we can make this as small as we like. Any guesses? Is it Cauchy? Is it not Cauchy? You think it should be? Why? You're just flipping a coin, or you have a reason? One way we could get some intuition here, I mean, in this case, we can actually look at the limit function. What's the limit function here? So what does this limit to? Okay, so you say 0. That's almost correct. For x not equal to 0, that's right. If x equals 0, then each one of these functions has the value 1. 1, 1, 1, 1, and 1 just converges to 1. So let me ask you again, is this a Cauchy sequence? Probably not, right? This is not, if there was a Cauchy sequence, it would have a limit in the metric space. This is not continuous. Okay, and we know that not convergent means not Cauchy. And we could check this stuff directly from the definition of a Cauchy sequence, of course. So suppose it is Cauchy. Pick any n star. Pick whatever n star works. And any n bigger than n star, and any other m that's also bigger than n star. I'm going to give you a particular choice. Right? If n star is big, then the distance between Fn and Fm should be small with these choices. Right? I've made a particular choice relationship between m and n, but that doesn't matter, and any relationship should work. So what's the distance between these two things? This is, okay, 1 over nx plus 1 minus 1 over 2nx plus 1. Okay, I put all this over a common denominator, and I get nx over nx plus 1, 2nx plus 1. The norm is the maximum value this will ever take over all x's. So this is certainly bigger than or equal to what I get if I take, say, x equals 1 over n, just to pick something. Okay, x equals 1 over n belongs to 0, 1, so that's an allowed thing to stick in there. And if you simplify this down a little bit, what's the numerator? The numerator is 1. Here we have 2, here we have 3, this is 1/6. In other words, no matter how big n star I pick, the distance between Fm and Fn can always be made bigger than or equal to 1/6. I can't force this less than any epsilon. So I can't force this less than epsilon for epsilon less than 1/6, no matter how big n star is. So again, this is not Cauchy. We showed in 2 ways. This is not Cauchy. And of course, if this was coming from some more sophisticated process where you can really guess at the limit, and you did this and said, this is not Cauchy, that means this converges to something not continuous. That doesn't make sense for the process I'm trying to simulate here. Then you'd say, back to the drawing board. I need a better model or a better algorithm or something here. All right, now we know with metrics that the concept we have of open sets and other things depends on our space, but also on the metric that we're using. Like we saw last class, the discrete metric gives unexpected results. And that would be true even if I put the discrete metric on all of R, right? And that's true for concepts of convergence as well. What you can conclude about convergence depends on the metric that you are using. So, for example, pens are failing me today. Let's come back to the discrete metric, but with a very familiar collection of objects. Okay, so this is our discrete metric again. So it's 0 if we are comparing the same object and 1 otherwise. All right, and now under this metric, let's consider the sequence 1 over n. Is this a Cauchy sequence? Yeah. No, why not? The distance between things will always be 1, exactly. So consider any n not equal to m, no matter how big they are, right? The distance between xn and xm is always going to be 1. I can't make that less than any epsilon. Okay? All right, and again, this is no matter how big we take these things. Okay, so this sequence is not Cauchy. Of course, it would be Cauchy if we were using our more traditional Euclidean metric. It's not Cauchy in this metric. Is it convergent? You're kind of nodding tentatively. You think it's convergent? But we already proved all convergent sequences are Cauchy sequence. Convergence implies Cauchy. Other way around, not necessarily, but convergence implies Cauchy. If this was convergent, it would have to be Cauchy. It's not Cauchy. This is not a convergent sequence. So, in fact, this sequence is not convergent. And it's because of the particular metric that we're using here. Of course, in a different metric, this very well might be convergent. It would converge to 0 in the Euclidean metric. But in this metric, this doesn't have a limit. And in fact, in this metric, I guess the only sequences that would be convergent are sequences that eventually just become the same constant over and over and over and over again. Because the only possible distances are 0, 1. So the only way to force things to be less than epsilon is to say eventually it's just always 0, 0, 0. Okay, so which metric you use makes a big difference, potentially, in what you're going to conclude about convergence. Motivation to use the right metric for your problem. But it turns out it's not that changing my metric a little bit is necessarily going to mean I get completely different results. There are a lot of metrics that, while distances between things will be different, they will still tell you the same thing about do things converge or do they not. These are called equivalent metrics. Okay, so if we have two metrics, are both metrics on a collection of objects A, then we could call them equivalent metrics if, not if they're the same, give the same distances between things, necessarily. And what we're going to say is that the ratio of these two things is bounded above and below. We're not going to have the ratios of these two metrics trying to go to 0 or to infinity. It stays under control. And that's enough to keep your concept of what is an open set, what does it mean for things to converge, under control. So if there exist some numbers, alpha and beta, that are positive, such that the ratio of these two things is always less than beta and bigger than alpha. And we'll exclude the case x equals y because we don't want to divide by 0. And then, importantly, so if you have a few metrics that are equivalent, then you can, they share a lot of the same conclusions. So what we're going to prove is that if two metrics are equivalent, then the open sets in your space are the same. In other words, if a set is open in one metric, it's open in the other metric and vice versa. And actually characterizing these open sets is really what you need to characterize all these other issues of convergence. If the open sets are the same, and we saw last class, like with the discrete metric, the open sets were not what you expected them to be, and now we've seen that actually also issues of convergence are not what you expected them to be. It's all related to the same thing. Once you have things that are equivalent, the open sets will all be the same. Distances will be different, but the open sets will be the same, convergence will be the same, and that means if you have a particular problem at hand, and you say, well, this part of my problem would be really much easier to prove using this metric. I would like to use this metric to prove that this set is open because it just looks easier, but now I go down farther down the problem and say, but actually establishing this as Cauchy would be a lot easier in this other metric. Well, if these are equivalent metrics, you can do that. You can mix and match. Use whichever metric is easiest for the stage of the problem that you're at, and know that your conclusions are still going to hold. So here is the main result, that if we have two equivalent metrics, on a set A, then they give us the same open sets. Okay, so proof, we want to show that if a set is open according to this metric, it's open according to that metric. So let S be open in one of these guys. Now what are we trying to prove? We're trying to prove that it's open in the other metric. So let me write down what it means for this to be open. All right, so we're going to choose a point, any x naught in our collection. We need to show this is an interior point. All right, we know it's an interior point according to this metric. We want to show that it's an interior point according to this metric. Okay, so let's write down what this means. It means there's some neighborhood of this point. There's things that are, if we take all the points that are within a distance epsilon of this, according to this metric, that neighborhood stays in the set A. So we know there exists some epsilon bigger than 0, such that this collection of such that, how will I write this? If the distance between these things is less than epsilon, then automatically this point stays in the set S. But X not be an S, sorry. Okay, this is just what it means for a point to be an interior point of S, according to this metric. Now I want to write a similar statement with sigma. I'm not going to probably keep the same epsilon here, right? Because sigma might make things bigger or smaller. So I've got to somehow take my epsilon and rescale it either by this alpha or by beta. So what do I want? I want to take sigma less than something to imply that rho is less than epsilon. Rho is less than, I guess, beta times sigma. So let's consider the neighborhood of points satisfying the distance between x naught and x is less than epsilon over beta. I'll rescale it by beta. And now what do I want to conclude? I want to conclude that this neighborhood of points stays completely inside my set. The only tool I have to do it is to show that this inequality implies this inequality. So we ask ourselves if that's true. We say, well, rho is less than or equal to beta times sigma. And indeed, we conclude that if we take this neighborhood rescaled, then indeed it will mean that we're automatically in this neighborhood, which means automatically x is in S. So we can say, great, S is also open in this other metric. And the converse is a similar argument. You have to rescale in the appropriate way by alpha. The other way is similar. Okay, so equivalent metrics, if we can prove this rescaling here, then we're kind of in business. Then we know that these metric spaces behave in similar ways, right? The particular values of the distances may be different. One point may be close, these 2 points may be closer together in one metric and farther away in another metric, but how much of a difference that is, it's controlled, and that controls the notions of convergence. Eventually, if these two things are getting close together in one metric, they're getting close together in the other metric, right? So if we have, by a similar student, if we have a sequence converging in this metric, then eventually the x ends and the x naughts are within epsilon of each other. That means it'll converge in this metric because there's just a rescaling, right? Eventually they will get close together. You know, it may be multiplied by a factor of beta, but beta times epsilon still goes to 0. Okay, so what are some examples of equivalent metrics? Is this just a game I've introduced and there's no practical equivalent metrics? The good news is that that is not the case. There are a lot of equivalent metrics. In particular, if you have 2 different norms on a metric space, those 2 different norms induce a metric, 2 different metrics, those metrics are equivalent. So metrics induced by norms are all equivalent metrics. And that means, again, you can do each step of your problem using whichever metric looks easiest. So what I'm going to do is take a metric on Rn, which has been induced by some norm, and what I'm going to do is show that this is an equivalent metric to the metric induced by the L2 norm. Okay? And if it's equivalent to the metric induced by the L2 norm, then it's also equivalent to the metric induced by any other norm, right? So L1 and LP would be both equivalent to L2, so both equivalent to each other. So then it is equivalent to the metric induced by the L2 norm. Okay, so I need to show something like this, where one of these is rho and one of these is the Euclidean distance, the usual Euclidean distance. What I'm going to do is just play with unit vectors. Unit vectors according to the Euclidean distance, according to the L2 norm. So let's start here. With x not 0. Okay, x equals 0 is the trivial setting, though. So this, this is already any vector, and now I'm just doing a rescaling, but we'll see that the rescaling pops out. This is a vector, but this is just a number, and numbers we can always pop out of norms at the end. So at the end of the day, if I have this inside of my norm, then I can pop this out, and I have norm of x, whatever x is.
What is the subscript of 2 for?
To indicate it's the L2 norm,
Okay.
because we know we have lots of different norms here. Okay, so what's our goal here? Our goal is to find something like this. Okay, this will give me what I want, because again, this is just a scalar down here, which pops out of the norm. So then I'd have norm of x divided by 2 norm of x. And then I just have to put in x minus y instead of x, and I get my metrics popping straight out. So if I can do this for x not equal to 0, I'm done. I don't have to do it for x equals 0 because equivalent metric says I don't have to do this for x equal to y because we know they're both equal to 0 at that point. Okay, so how do I want to define these things? Well, I'm sticking a bunch of different values into my norm here. They're all unit vectors. And what I really want to do is say, what's the biggest value this norm could ever take on a unit vector, and what's the smallest value this norm could ever take on a unit vector. So that's what I'd really like to do. I'd like to say, my domain is all the unit vectors. What does the norm do? Is it bounded? That's really our question. If I stick unit vectors in here, does this norm stay bounded from above and from below? So my domain is the unit vectors. And what I want to do, and I need to decide if I'm allowed to do this.
Is this the L2 norm equal to 1?
This is the L2 norm being equal to 1. Because if I look at x over the L2 norm of x, this argument here always has an L2 norm that's equal to 1. Yeah. When I say unit vector, I mean, that's important clarification. Because something can be a unit vector in L2, but not in any other norm. So what I really want to do is I really want to define my alpha and beta this way. Alpha just to be the minimum value of the norm, and beta to be the maximum value of the norm. All right. Bounded maxes and mins don't always exist. We know that. What do I need to be true in order to be able to do this? What's the setting on which I'm guaranteed that my function takes a maximum and a minimum? Yeah.
Closed and bounded.
I need a closed and bounded domain, and what should be true about my function? It should be continuous. Yeah. So those are what I need. I need a closed and bounded domain. That seems okay. Okay, I'm looking in Rn. I'm getting just the points on the unit circle here. All right, that's a closed set. It's a bounded set in Rn. So that's fine. So S is closed and bounded. So now the issue is N continuous? If N is continuous, the max and min will exist. Okay, so let's try to show it's continuous. We know what it means for a function to be continuous. I mean, in this is just a real valued function, right? A real valued function on Rn. So we're not doing any crazy magic here. So let's pick an epsilon. And what do I want to look at? I want to look at n of x minus n of y. And I want to show that I can make that less than epsilon as long as x and y are close together. What's one of our favorite tools for dealing with these kind of inequalities when I'm trying to do this? Adding and subtracting things, yeah, that's always a good one. What else? What are our other favorite? Triangle inequality. Triangle inequality works here. Okay, so I can do this, which is also, you can think of as adding and subtracting things. And this is nothing but the triangle inequality. This is just saying n of x is less than or equal to n of x minus y plus n of y. So this is just a rearrangement of the triangle inequality. Where I've added and subtracted something to x to get what I want. All right, now I'm going to break this down a little bit component-wise. So let's look at what all the components of these things are. So I have the ith component of these things multiplied by a unit vector pointing in the ith dimension. Right, so EI is a unit vector. In the ith dimension. Okay, so this just says I have x1 minus y1 in the first direction plus x2 minus y2 vector in the second direction. This is just splitting this thing up into its components. It's nothing but that. But the fact that I'm adding things up inside my norm means I can keep using my triangle inequality. I don't have many tools to work with here, so I just have to keep using triangle inequality. So if we do triangle inequality again, we can say, well, the norm of the sum of a bunch of things is bounded by the sum of the norm of the individual things. All right, I've maybe about exhausted the triangle inequality at this point. What else do we know? There aren't very many things we know about norms. Yeah?
The norm of EI is 1?
Well, I guess the 2 norm of EI is 1. It probably depends how we define our norm here. So, right, all we know about n is that it is some norm. There's basically 3 things we know about norms, right? 3 properties norms have to satisfy. We've kind of used up the triangle inequality. What other properties do we have? They're positive. Okay, so this is positive. One more. I can pull out scalars, exactly. So what do I have here? I have a scalar times this vector. I can pull out the scalar. So I pull out the scalar in absolute value. Okay, so here I pulled out the scalar. All right, so we're getting actually closer here. We're trying to get this less than any epsilon. Now, this is for x minus y sufficiently close together, so I'm allowed to control this somehow by my delta. And this is actually kind of nice. These are constant vectors, right? What happens here does not depend at all on what my x and y are. It's always the same. Okay, so this is just some fixed numbers, whatever they are. So I'm going to write it like this. I'm going to rewrite this sum as an inner product. So the first vector has the components xi minus yi, just the sizes. The second vector has all of these components, n of ei. So n of e1 all the way down to n of en. And once again, this is a constant vector. It doesn't care what x or y are. It doesn't care what epsilon is. It doesn't care about anything. It's just a single constant that depends only on the particular norm. So what do I want to get? I want to make the distance between x minus y appear, right? Because I want to make that less than some delta. So how do I make the distance between x minus y appear here? Yeah. Something along the lines of triangle inequality. Okay, there's related to that inequality. What's one of our fundamental inequalities that comes along with inner products? Do you remember? Cauchy-Schwarz. All right. So this is going to be bounded by, all right, whatever is the 2 norm of this object. I don't know what it is, but it's a number, right? This is a constant vector, so it's always the same number. Times whatever is the 2 norm of this, which is just x minus y. No, 2 norm. Okay, so this is true for some k, which is positive, right? The norm is always positive, so all of these components are positive. They're not zeros. And what was the question? The question was, could I make this less than epsilon? Right? We started way back here by saying, we're trying to show this is continuous, n of x minus n of y. Can I make it less than epsilon if x and y are close enough together? And the answer is, well, sure, as long as we take x minus y to be less than epsilon over k. So we've recovered continuity of this norm. Okay, so norms are actually continuous functions on our end. That means alpha and beta are well defined. And okay, excluding this, alpha is the minimum value this will ever take. Beta is the maximum value this will ever take. So this is certainly a true inequality. Okay, so alpha and beta, which are greater than or equal to 0, are well defined. Can alpha be 0? If x is 0, all right. We said x is not 0, right? We're just sticking unit vectors in here, right? The norm acting on a non-zero vector is never 0, okay? So we have this function that is always strictly positive, and it's defined on a compact set, closed bounded set. So the minimum is also going to be positive. Right? The minimum is attained, right? The minimum is the value at some unit vector. All right, so since the min is attained, we know that alpha equals n of u star for some u star. U star is not the 0 vector, right? So since we're looking at unit vectors, U star is certainly not the 0 vector. So that means this has to be a positive number. So what do I have? If I put this all together, we have that alpha is less than or equal to the norm of anything I like. Let's say x minus y divided by the 2 norm of x minus y. Okay? Constants come out. And this is precisely the ratio between the two metrics. Okay, alpha is positive, and by the same argument, this is less than or equal to beta. And that's a statement that we have equivalent metrics here. So what is our conclusion? The conclusion is the metrics are equivalent. So if you're playing in Rn and we have tons of norms on Rn, we've written down lots of them, we've written down infinitely many of them. Again, they all induce metrics. These metrics are all equivalent, so pick and choose which one you like. And they will give you the same kinds of answers about open sets, about convergence, about Cauchy sequences. You know, you're safe.